invite Ambuj. Somebody can take the microphone to them.
Hello everyone, I am Ambuj from IIT Jodhpur. Firstly, I would like to thank for such a nice and wonderful talk. My first question is we have talked about this question-speaker model, and so the question is like how PVR theorem contradicts or rejects this question-speaker model.
So if you look at the question-speakers, if you look at the question-speakers model, so if you consider any two non-orthogonal states, then there will be common ontic state. Yeah, you look at the sphere and you can easily find it. Now, in PVR theorem, what they use, they take two independent sources and collect two particles from the source, where the source produce with, let's say, with half probability 0 and half probability plus, where 0 and plus are non-orthogonal state. Then, if you collect two particles from the source, then with some finite probability it may happen that both these lambdas, ontic state, comes from this intersection region. Then actually, if they comes from intersection region, then actually the logic tells that you should not be able even to discard a state. At least, I am not only telling that it cannot be distinguished, but it cannot also, you cannot also reject one of these states. Okay. Now come to the quantum mechanics. The two particle has been collected, but quantum mechanics give you a nice thing that you can measure in an entanglement basis. It looks like Bell basis, it is all Bell basis, but not in the usual form. Then it is complete basis, so you can perform a measurement and you will collapse on one of these Bell state. And the nice thing is that the four possible states that you may get, one of them is orthogonal to at least one of the Bell bases. Then whatever result you get, you can tell at least one product, this particular product state has not appeared. So in each and every case, you can reject one of these. Sometimes it has been given a different name, anti-distinguishability. Yeah. So always you can reject a state. And if you believe in epistemic model, then at least in some cases you should fail. But in quantum actual measurement, you will not fail. That is the contradiction. So one comes to the conclusion that psi must have a ontic nature.
So there is a follow-up question from that. So for a psi epistemic theory to be recognized by our community, what will the possible benchmarks that it has to pass that it is fully accepted?
So you're asking what would make people accept the psi epistemic point of view?
Yeah.
As you know, in quantum foundations, everything is controversial. So probably the answer to that is nothing. Despite appearances, I'm actually optimistic that something called the correct interpretation of quantum mechanics exists, right? And that when we have it, we'll know it, and we don't have it yet. So to my mind, the answer to that question is, once we've found the correct interpretation, if it's psi epistemic, then people will eventually accept that. For me, being psi epistemic seems to be a good working hypothesis, because first of all, I think that none of our existing interpretations are right, and since none of them are psi epistemic, that gives me something to work towards. And secondly, I just think that the psi epistemic interpretation explanations are sort of so useful to my thinking. They're useful to my thinking about quantum information and things like that, that I just think that it's going to be more explanatory if we are able to have this kind of interpretation. So for me, it's a working hypothesis. I don't say psiontic interpretations are ruled out. They clearly aren't. I don't think that I can persuade people who are strongly convinced of a psiontic point of view. I do think I can convince them that some of the arguments they use for it aren't great. So, for example, people will say you've got to be psiontic because of interference. And, well, I have a whole paper on that. So, you know, I think there are some arguments that aren't right. There are probably some arguments for the psi-epistemic point of view that aren't great as well. One of them I'll just allude to, because you mentioned the measurement problem and the collapse of the wave function. Well, it would be nice if we could have a psi-epistemic point of view where collapse was just basically updating of information. But we can't, because there's also an ontic disturbance that goes on, right? You just have to do 3 Stern-Gerlach measurements in a row with different direction in the middle, and you see that you can get a different measurement outcome. So the measurement projection postulate cannot be just updating of information. So somebody who goes and says, the reason I believe in the psi-epistemic point of view is because I want the projection postulate to be updating of information, that's a bad argument, right? Somebody who goes around and says, I think nature is psiontic because quantum interference, that's a bad argument. So we can identify bad arguments and hopefully move the debate on, prove things, but at the end of the day, the question is unresolved until we have the correct interpretation, I think.
Thank you.
Yeah. So this is mainly for the student. I'm saying you look very interesting things. We have few discussion, few talk on Bell's theorem, and today this PBR theorem. You look into the Bell's theorem. So Bell's theorem, it all are prepare and measure. So Bell's theorem, your state is entangled, and two party Alice and Bob, they are performing product measurement. Alice is performing measurement on the one part of the Bell state, entangled state. Bob is performing measurement on the other part of the entangled state. And the resultant statistics say that no local realistic model will be there. Now come to the PBR things. Cochin-Specker model already gives a psi-epistemic interpretation for qubit state only for projective measurement. But how PBR say take two different preparation? Of course, we have some assumption that at ontology level, their ontological distribution will be product form. And they are performing entanglement basis measurement. Now you see Bell's theorem and PBR theorem, this role has been reversed. Bell's theorem, entangled state, product measurement. In PBR theorem, it is product preparation, but entanglement measurement. That is, so Nicholas in his talk he was telling, no, measurement, it has measurement, deep problem of measurement collapse is there, but measurement itself reveal lots of peculiarity. PBR theorem is one such example. This entanglement measurement actually discarding, under the assumption of preparation independence, discarding this epistemic interpretation.
Thank you. Neelaj?
All right, hello, I'm Nilaj from ISA Mohali. My question is mainly towards Professor Guruprasad, but if the rest of the panel members want to add something, I'd be delighted. So I keep coming back once again to contextuality, I know, but so using the notion of measurement non-contextuality, you can derive bell-type inequalities. And it turns out that there's a paper where, yours only, where you have worked out the bell-type inequality for a single spin-half particle. And it turns out that the bound, the non-contextual bound, is the same as that one would derive using standard Bell's theorem, where you have assumed the notion of local realism. So how do you kind of describe that the fact, or describe in the sense, how do you kind of explain the fact that two different worldviews, non-contextual realism and local realism, are kind of giving me the same bound on the Bell-type variable? That's the first part. I have a few more questions. You can answer that, yeah.
If you look at this setup, so it is a qubit in interferometric setup.
Right.
Now this interferometric setup is actually isomorphic to qubit, like C2. It can be fully described in C2.
Right.
So basically the system, it is using 2 degrees of freedom of the same particle, same qubit, but both are C2. So
Right.
basically it is C2 cross C2. And this 2√2 bound is coming from this Hilbert space structure. So it is mathematics cannot understand whether you are using these degrees of freedom or that degrees of freedom.
Right.
So you will derive this Bell's inequality by assuming that spin measurement will not disturb result path reality, and path measurement will not disturb spin reality.
Right.
So here actually it is not, you cannot use locality. So you have
Right,
to tell
because
it
it's single part.
non-contextuality. And these assumptions will derive the same Bell's inequality, and violation will be given by 2√2, because basically it is C2 tensor C2.
Right. I understand. So since the mathematics is the same, so it gives rise to the same bound. So on the same line of what you said, 2√2, so kind of like we have a bound where we say that the Seidelson's bound, where we have that quantum mechanics can give us a maximum value of 2√2. Is there something like that in this formalism as well, using this notion where we use a single particle entangled state? We put that in the Bell variable, we calculate the correlations. Yes, it comes out to be 2√2, but is there a proof that that's optimal or that's maximum quantum mechanics can give us?
It can be derived in many ways. So by using simple algebra also you can find it. But there are some principles like joint measurement and non-contextuality. You can use this concept to derive that it is 2√2. But of course, information causality will not work here.
That was actually my third question. So is there an information causality like thing
you
going
cannot
here?
apply this.
Right. So it does not apply, right? Yeah. Okay.
But probably there is another concept called local orthogonality.
Okay.
That should work here, because that doesn't require the space-like distance kind of things. This local orthogonality, of course, it has to be used in multi-copy of this probability distribution. Then asymptotically there is a claim that it will give this 2√2 bound. That approach should work here also.
Okay. Local orthogonality.
Local
Okay,
orthogonality,
I'll
or
check that
in
out.
literature you will also find by the name of exclusivity principle.
Okay. Thanks a lot.
Thank you. Soumya Jyoti. Just tell us where you're from and answer.
Yeah. So I am Soumya. I am from IIT Jodhpur, and my question is to Professor Leifer. So in the last slide of your presentation, you talked about some applications in quantum information. So what kind of applications they can be?
Okay, so it's my strong belief that if you prove a no-go theorem about ontological models, then you can come up with some kind of information processing game that exploits it. You can do that here, but they're very artificial, right? Because what you want to do is exploit the fact that if you've proved that the state is psiontic, then any classical simulation of that is going to necessarily reveal information to, say, an eavesdropper that allows you to determine the state. Right. So that's the idea, to exploit something like that. Right now, there aren't any really interesting applications of the proofs of Scientology itself. There are applications of the related concepts that have gone into the proofs. So in particular, this anti-distinguishability that's used in the PBR proof. There are various communication complexity protocols and things like that that have been proposed that use that as the basis. Again, they're a little bit artificial. They're not something that you would come up with unless you already knew the concept. But in principle, you can do these things. It'll be nice to find a truly useful application that people in quantum information would actually like to pursue, but that's still open.
Okay, sir. Thank you.
Yeah, can I add?
Yeah, sure.
So I'm not sure, but I just also want your opinion also. As you said, that if I have a this shy epistemic, completely shy epistemic model, in a sense it gives, it indicates towards a efficient classical simulation of the quantum phenomena. So in that direction, so for the student I am just telling that, let's say we play this teleportation task. So Alice is given an unknown state, he has to reproduce the state at Bob's end. As we know that classically we cannot do that due to the no cloning theorem. But we require a quantum resource, means if we have entangled state and 2 sieve it, then that can be perfectly done. But consider a little bit different scenario, that is called Alice is given the knowledge of the state, means Alice knows the state. Now the aim is at Bob's end, Bob has to reproduce some statistics performed on the state. Of course, Alice can send the qubit state, known qubit state to Bob, and Bob will do that. But can we try to simulate it classically? Only classical means by shared correlation, classical correlation, and with some finite communication. So there is an interesting work by Montina. He has shown that if a maximally shy epistemic model exists, then such a efficient, by efficient I mean finite communication classical model is always possible. And he has tried to argue that the converse of this theorem also true, there might be some assumption is going on. That is one way of showing that, okay, understanding epistemic, so this is a kind of simulation things. This communication scenario, I want to simulate this quantum behavior just by classical means. So that kind of understanding, this Shiontic epistemic theorem gives us better understanding of the quantum world in that sense.
Two comments on that. I want to make just 2 comments on that. So the first, it may seem like maximally psi epistemic models would be more efficient in terms of communication. And it's true. It's really non-obvious, though, because you have, if you look at the Cauchy-Specker model, the state of reality is still in the continuum. It's a vector, and it can take any direction. And in fact, we have the hard is excess baggage theorem, which tells us that that must be the case. So the efficiency is coming from the fact that you don't have an arbitrary probability distribution. So there's actually a certain amount of information compression that can be done on that. But it's really non-obvious, and actually the Montina results are kind of deep. So I recommend, if you're interested in this simulation angle, I recommend looking at them. The other thing is, you know, if I want to say an application of Scientology in particular, you know, here's a way that you can get an application of any no-go theorem. The game that you have to play is reproduce the statistics of quantum mechanics, right, using the fewest classical resources. Then any obstacle is any obstacle to a specific kind of model is an obstacle to that kind of game. It's not a very interesting kind of game. So, you know, when I say applications, for sure you can come up with applications like contrived. I don't want to call it contrived, but you know, ones that aren't very, very specific to this problem. What I want to see is something that's really powered by Scientology in kind of a very direct way, and is also useful, right? That would be the reason for being interested in it. And since, you know, I put up that hierarchy in my talk, you know, you would have thought that things that are higher up in the hierarchy should be more useful than things that are lower down. Okay, hasn't proven to be the case. You know, Bell non-locality is extremely useful in cryptography and things like that in very natural problems, but you know, we don't have that necessarily for things that are higher up.
Thank you. Nikhil?
Hello, sir. Myself, Nikhil from ISER, Kolkata. First of all, thank you for the thought-provoking lectures. So, I have 2 questions. So, first question has 2 subparts. First question is regarding the postulates of quantum mechanics. The first postulate, like we all know, we all studied anyway. The state of quantum mechanical system is specified by wave function, which contains all the information of the system. So this one, but if a student asks you like, how much percentage should I believe in this postulate? And if the answer is not 100%, under what conditions we should be skeptical about this postulate? And in the second part of this first question is, Yeah, means another thing is the information. All it contain all the information of the state. So in that, whether should we consider this wave function contains this information, all the information of the system as a absolute statement, or does that, or what does it really means about the information? Because that time when they are postulating, they didn't have knowledge about entanglement, all these things. But what would be your arguments, or can you elaborate on ontological and epistemological aspects considering current state of knowledge? And finally, like, can you recommend some references for which at present state, which are rigorously recent references which have rigorously examine the postulate of quantum mechanics with present understanding? Thank you. So it has 3 subparts. Okay.
So if you follow if you have followed this lecture by Professor Leifer, then he has written about operational theory, then underlying theory. So operational theory means you perform experiments, get some new results, and based on these results, you are trying to construct a theory such that experimental results can be reproduced. Now, when we tell that the state contains all the information, then it has to be qualified. It keeps all the information that nature allows you. So in that sense, if you consider the quantum mechanics as operational theory, then psi contains all the possible information that nature has to keep, that nature allows. In this sense, you have to see it. Now, why we are doing all these hidden variable theory, ontology, epistemology? We are trying to see whether, in principle at least, it is possible that actually there are information about its observables, and psi just is a probability distribution over those actual informations. Whether this kind of model may work. But this is all about our lectures, that at least psi epistemic theory is in danger. Maybe psi epistemic theory cannot reproduce all these features of quantum mechanics. Like if you consider KS, Cauchy-Specker model, it correctly reproduces Born probability distribution. But in the PBR you see that I saw something where quantum mechanics gives some results, but psi epistemic theory cannot reproduce. So in this way you have to see that there is operational theory, and mathematically at least we are trying to construct some other theory where reality is there and it also reproduces quantum mechanics. Now we are dealing with this kind of theory, whether finally it can reproduce quantum mechanics or not. In this way you have to look at the questions. Yeah, that's it.
Okay, so I think it's helpful in this context to recognize that although we talked about 2 kinds of state, we talked about the ontic state and the epistemic state, there's actually 3 kinds of state in play. There's the ontic state, the epistemic state in terms of information about the ontic state, and then there's the operational state, which is also an epistemic state, but it's epistemic, it's knowledge about the potential results of future measurements. All 3 of those exist in these kind of theories. Now, the postulates of quantum mechanics are only really about the operational state, and there is no strong disagreement about those postulates. However, so if you state them sufficiently carefully, then there's nothing to disagree with. However, if you read an undergraduate textbook on quantum mechanics, then almost every author overinterprets. So when you say something like the quantum state contains, I don't know exactly the statement, but all possible information, well, that's a controversial statement and isn't really needed for the postulates of quantum mechanics. You can say it contains all the information that the theory gives us about the operational predictions, right? That's fine. So if you state these things in a subtle enough way, then there is no disagreement on the postulates. But most authors overinterpret in one way or another. I don't know if that's really a bad thing, because if I tried to write a textbook on undergraduate quantum mechanics, I would probably get so obsessed with fine distinctions in the foundations that are important to me that the undergraduates would get confused. So I think there's always going to be a certain amount of this. You have to sort of read between the lines between what is said in a textbook about the postulates and what is actually used, right? How we actually use those postulates. And ask yourself, is this part of the postulate actually used at all when we do our quantum mechanical calculations? So I've made it a bit more about pedagogy than anything else, but I think that's part of it. You also said something about deriving the postulates. Could you clarify what you mean by that?
Yeah, it's not about deriving. It's about I was asking, means how much if the postulates, if we should not believe them 100%, when at what conditions we should be skeptical. So this was.
I mean, when we state a physical theory in the first place, there's often caveats. If they're stated sufficiently carefully, they're fine. The problem is that they're not always stated sufficiently carefully, and it's not just stuff to do with this, right? So, a textbook might say an isolated quantum system evolves unitarily. Okay, most people are happy with that. It might say somewhere else a quantum system evolves unitarily, right? That's not quite correct. Right, so the point is that I don't think there's a case where we shouldn't believe the postulates, at least if we think quantum mechanics is still a correct theory. But there are cases where you have to be careful in how you state them.
So,
Thank you.
One more in continuation. Just want to tell I read some of Heisenberg books, so this physics and beyond and physics and philosophy. So there states about concepts in classical mechanics we use position. We know, we intrinsically we understand when in quantum mechanics when we come, we intrinsically understand what is position, but as such in theory, when for absoluteness of theory, the position, the concept becomes little bit vague. So there he was telling about this epistemological arguments. So finally the things rely upon the language of communication something. Can you comment upon these thoughts of Heisenberg? Or is the question is clear, or should I elaborate? Okay, I will just tell. For example, Heisenberg, he has argued in one of his statements in classical mechanics, when you define position and momentum, we know and we perceive also position, what is position, how the object is moving. And another one is when we carry these same notions to quantum mechanics, like position and momentum, somehow we understand by intuition what is position and momentum. But when you consider in quantum theory, the position itself or the momentum, because it doesn't have, because in experimentally they are they are related, we cannot really define position and momentum. So there he brings about this state of knowledge, all these big terms. So, and he talks about finally we cannot carry forward much the state of knowledge, we cannot carry forward because these concepts are a little bit defined with its approximations, I think. If you can comment upon this understanding, or
yeah, let me try to, though it is not very clear to me. So in classical world, if you consider a particle, its state is position and momentum, and whatever other dynamical variable you consider, they are function of position momentum. So position momentum is the state itself of the particle. Now, how quantum mechanics was born? Because based on this concept, classical ideas and its corresponding dynamics, you cannot explain so many things. That's why people tried for a long time, and with some what do you call this, through a correction process, so finally in 1926 they constructed the theory. Now you have to, after it's being constructed, you should look at it as it is. So it is, the state is not position momentum. If it is position and momentum, then by that thing, if you could explain interference phenomena, then it's okay, classical mechanics will go on. Just that and some other experimental result they cannot explain. That's why they have to adopt a new operational theory. And in that operational theory, position and momentum has not the status of being a state. So a state becomes wave function, that means vector in Hilbert space. We may not like this kind of description because in classical world, whatever state description, dynamical description, we can visualize to some extent. But here we are not satisfied that quantum mechanics starts from mathematical description. System is associated with a Hilbert space. Of course, we cannot visualize it, but we have to accept. So so position momentum in quantum mechanics is some observable which you can measure. And after measurement, some position or some momentum will be revealed. That's all. And the state will be updated according to von Neumann projection postulate.
Thank you, sir.
Thank you. Aryaman?
Actually, can I briefly comment on that?
Yeah.
So, I mean, really, the kind of question you're asking there should be addressed by a historian of physics, like to really analyze what Heisenberg thought back in the context he was writing those things. My usual attitude to these things is, we spent too much time worrying about what Heisenberg thought, what Bohr thought, what Einstein thought. There's value in those things, but there's also value in, let's sweep away some of those concepts and try and think about these things afresh. So that's usually what I try to do. You will have noticed in my talk, I didn't quote any of those people at length, which is uncommon for a Quantum Foundations talk. It's also deliberate. But the other thing is, so if I put all that to one side, I mean, Heisenberg, his opinions on quantum mechanics are known to have changed. They're known to have conflicted with Bohr, and they had lots of debates. So Heisenberg, over the course of his career, shifted from a point of view which was more like systems have positions and momenta, but we can't access them, and there's some disturbance caused by measurement, a more sort of classical-like epistemic position, to viewing the Heisenberg uncertainty relations as more of like an indeterminacy relation, right? It tells you that, positions and momenta don't have values at the same time. Not that they're just unknown, but that they don't have values. So he shifted through conversation with the Bohr to a position more like that. What I would argue from a modern perspective is that a lot of that argumentation was, to my point of view, sort of insufficiently rigorous, right? They didn't consider the full space of possibilities. They were just sort of interested in getting a view that worked, getting a view that didn't sort of overcommit and that worked. So I find more value in like trying to sort of step back from all of that stuff and work out, what can we really rigorously prove, than spending a lot of time analyzing it. But there is some value in those ideas, but I don't know if you can really say too much about the modern results from that.
Professor T.P. Singh, want to...
Could I, come back to this? It's the right time, I think, to make... So we could say that classical mechanics is Q-ontic because the position and momenta are dynamical variables embedded in space-time. I know what is space-time, and let's say it's ontic, and the position also is in space-time. Now go over to quantum mechanics and trouble begins. If I want to say that psi is ontic, let's see it in the context of the famous double-slit interference experiment. An electron leaves the electron gun. It's still a particle traveling through space-time, but to explain interference, I must associate to it a complex number-valued wave function. And now the problem is, we say there's a wave that is going. What is that wave of? Some people say it's the probability wave, but probabilities don't travel in space-time. And if I want to say the wave function is the wave, I again have a problem because wave function is complex and we can't imagine square root of -1 going through space. So to my understanding, the difficulty lies in when we go from classical to quantum mechanics, we have made position and momentum into operators, but we have carried through space-time as if it continues to be classical. Suppose we allow in quantum theory, we say no, in quantum theory, irrespective of energy scale, space-time is also complex number valued. Then I'm comfortable with thinking of a wave function which is a complex number traveling, it's a function of a complex space-time. So it just takes two different values on a complex space-time, and that helps me understand psi as psiontic in the same way that Q is Q-ontic. I should modify space-time also. It's illegal to keep space-time classical in quantum theory, except as a very good approximation. But it is that same approximation which lands us into so much trouble. And I don't know if the founding fathers of quantum theory thought of this or Einstein thought of this, I don't know. So I would like your reaction to this and also anyone in the audience. And just add a question. What happens if I work with the Heisenberg picture in quantum theory, with Heisenberg's equations of motion? In some sense, they might be still Q-ontic, but I don't know how to describe collapse in the Heisenberg picture. So if you have some thoughts on that, if you could kindly comment.
Maybe I'll respond to the first of your two questions, then maybe someone else can think about the second one. So I think that there's an important conceptual thing to get straight here, right? It's what are we doing when we talk about realism, about quantum mechanics, right? We already know that like standard non-relativistic quantum mechanics is not the correct theory of nature. So if I say in non-relativistic quantum mechanics the wave function is real, I'm clearly not saying that in the real actual world that's what's real, because I know that quantum field theory is a better approximation. So when we talk about realism, about scientific theories, we're never talking about what's really real in the actual world. We're talking about more the internal explanatory structure of that particular theory. So you're asking yourself a question something like, if this were the real full physical theory of the world, what would it be like? And we generally have the idea that for theories that are successful, there should be some story like that, right? So if you say, well, what would the world be like if Maxwell's electromagnetism were the true theory of the world, then you would probably say things like, okay, there are these fields, E and B fields, and this is how they behave, and so forth, right? So given that standard quantum mechanics on ordinary space-time works over such a sort of range of applicability, even if you think it's not fundamentally the correct thing, it does seem to me that we're owed a story about what's going on if that were true, and that somehow that story should help us determine how to think about the theory more generally, and maybe extend it to things like complex space-times or other things like that. But I don't think it's, like, I've never found it helpful when thinking about how to understand quantum mechanics to like start by generalizing it. That, to me, that comes later, but that's just my thoughts on it. Anyone want to respond to the second part?
So I just wanted to add, but not from this angle, because I did not understand very clearly that in the Heisenberg picture, how do you model your collapse and so on, or let's say even to, without having a dynamical description, but still how you say something is happening there. Just to give you an intuition that you can also think of superpositions in evolutions. For example, yesterday we talked about quantum switch. It's actually a superposition of evolution. And when you have that superposition, I can also collapse my evolution to a particular evolution, which is one of these superposition, let's say, bases in the level of operation. So all these things on the level of operators or evolution, you can legitimately define, and not only that, even the Born rule will prevail there. Yeah, so just to add that.
In that case, in the Heisenberg picture, quantum theory is Q-ontic. Why do you have to worry about psi?
Maybe I'll respond to this part. So, right. In the Schrödinger picture, you might say, oh, the Schrödinger picture is psiontic because the state is psi and that evolves, and certainly if you interpret it naively, that's what it looks like. Then you might go to the Heisenberg picture and say, well, in the Heisenberg picture, I'm dealing with these operators that represent the observables. So those are the central characters of the theory, and so if I interpret it naively, those are the things that are physically real. But those things are operators, not quantities, right? So if you say that, you're saying something like the world is made of some sort of operator stuff, right? And saying that the world is made of some sort of operator stuff is just as confusing to me as saying that it's made of wave functions, right? And so there's a reason why when we study these things and try and prove theorems about them, we don't start with the formalism of quantum mechanics. Note that I started with the notion of an operational theory. I started with the notion of things that are experimentally accessible, and I look at what the quantum predictions are. I don't specifically, say anything about a priori about, what does the state represent, what do the measurement operators represent. All I say is that there's some physical state between preparation and measurement. That thing may have more than one mathematical representation, by the way, just as, how I could write Lagrangian mechanics instead of Hamiltonian mechanics, and I'd come up with a slightly different view of what the ontology really is. But those things can be sort of, they're isomorphic to each other in a certain sense under the right conditions. So the same is going to be true here. When we say the wave function is real, what we mean is the thing that corresponds to a pure state preparation is somehow, the information about what pure state preparation was done is present in the system. That's what it means. It doesn't necessarily mean that, there's that the entity as it exists in the Schrödinger equation has to be thought of as literally real, right? So I think it's important to distinguish like formalism from ontology. What we're trying to do is unscramble, like as Jane says, we're trying to unscramble the omelette of ontology and epistemology. Whatever the quantum formalism is, I don't think we can assume we should ever assume that it's a direct representation of the ontology. That's just my way of going about these things.
It seems to me that quantum theory is half quantum and half classical.
Okay, now it is Girish.
Yeah, hi. My question is again in line with what Professor T.P. Singh asked. So there's this issue that the wave function of a multi-particle system lives in a higher dimensional configuration space. So this fact sort of points me to think about an epistemic interpretation rather than an ontic one. Because, so for instance, even in classical mechanics, the Lagrangian of a multiparticle classical system lives in a higher dimensional configuration space. But that's not problematic because we don't really think of the Lagrangian as something real. But when you say that psi is an ontic entity that actually exists out there, then it has to live in a higher dimensional configuration space and not really in the real three-dimensional space that we think of. So how does one reconcile this way of thinking?
So, there are a lot of great arguments for the epistemic view of quantum states, and that's one of them, right? You know, that's one of the reasons why Schrödinger had a problem with you know, the quantum state being defined on configuration space. So how do you reconcile it? This issue comes up not just in PBR, but all over the place, right? So if you think about Bell's theorem, and you say, well, what does quantum mechanics say about Bell's theorem and non-locality? You could answer in the following way. You can say, well, quantum mechanics itself, like standard quantum mechanics, says nothing, because it involves a state vector that does not live in space-time, okay? So it doesn't tell you anything about what's going on in space-time, and so therefore I don't judge one way or the other. People don't normally say that, though. They normally somehow think of the two-particle wave function as belonging to at least to the regions of space-time where the experiment's being done. And people don't normally, even though it doesn't live in that space, people don't normally have strong objections to thinking like that. Maybe they should. But again, I think the real answer to that is sort of, it's a question of abstractness, right? Clearly, if you're going to have something like a psiontic theory, then the things that exist in space-time, if there are any such things, aren't, you know, just the usual variables. So we have to say that between the preparation and measurement, there is some entity somewhere present there that's isomorphic somehow to that quantum state on configuration space. It's not necessarily that thing in itself, but something that encodes the same information. It's a large amount of information because you're on configuration space, and you're right that the more natural thing to think is that that thing is something like you know, a function of the configuration of the system. So it could be like a dynamical law, like you mentioned with the Lagrangian, or it could be something epistemic. That's natural, but that's why the no-go theorems are surprising, right? If the no-go theorem coincided with your intuition, then it wouldn't be an interesting thing. So the fact that these things seem to be pushing us towards thinking of this as a state of reality, even though there are so many reasons for not thinking that, is interesting. And you know, it's one of the reasons why I personally am still interested in trying to preserve the psi-epistemic point of view, even in light of these things. So for me, all of these results, Bell's theorem, PBR, they push me to think that there's something wrong with our framework for talking about realist theories, rather than pushing me to saying there's non-locality, there's contextuality, there's real wave functions in nature. I would still prefer to say, you know what, I'm going to step back from like a full-blooded realist account of the type that we've been talking about and see if I can try and do something more exotic. So that's the way that you can try and save those sorts of intuitions.
There is a question from there, yeah. Who has the microphone?
Thank you. So actually my question was partially answered in the previous discussion. So I'll just rephrase it at the end. But yeah. So why don't these models try to explain the quantum postulates and instead target very specific quantum phenomena like state indistinguishability or no cloning? Because if you went for the postulates, then you'd be able to derive all other quantum phenomena. So I understand that you're trying to reproduce the measurement statistics of quantum theory without using them. But I'm talking about a stronger reduction from these theories to the postulates, instead of specific theories to specific phenomena like no cloning. So part of this was already answered. So this is my rephrase question. What is the motivation for modeling specific constraints like indistinguishability and no cloning?
I mean, I think it's two sides of the same coin. It's not correct to say that there isn't work on deriving postulates, right? That there is, so especially from an operational point of view. There's a lot of work on that. But the motivation and the goals here are slightly different. You're saying, can reality be like this? In order to disprove something, I only need a counterexample, right? I don't need the whole theory. So I just need to find some set of predictions that doesn't support that. So you can think the reason why we're focusing on specific predictions rather than the whole postulates is just because we're finding counterexamples to things. Think of it that way. But there is the other side of the work, which is to say, okay, in light of all that, how do you actually construct the theory? How do you understand how you construct the theory? And, but I view that as a different question. But people do work on that too. It's not correct to say it's that.
So how would you move beyond specific phenomena, like indistinguishability?
Well, I mean, what do you mean exactly? You mean you want to derive all of the postulates of quantum theory from what?
From your like epistemic or from psiontic point of view.
Well, okay. So let's consider something like Spekens toy theory, right? Spekens toy theory is based on principles, and it gives you a whole method. It gives you more than like one thing. It gives you a whole theory. That theory happens to not be quantum theory, but it is a theory that's quantum-like in many ways. So what you could do is say, okay, the kind of principles that theory is based on, I want them to be true of quantum mechanics as well, but I'm going to have to give up some of the structure. I'm going to have to try and apply those principles in a different context. So something like the idea that there's an epistemic restriction that has to be formulated, and we're going to try and derive things from that. That could still be done, but it's not clear exactly what structure you need to do this on. You need to give up something. But obviously, I think if we knew what that was, if I knew what that was, I'd be working on it.
Thank you.
Yeah, if I may just add to this. So you see, in Spekens toy theory, it reproduces many phenomena of quantum things like no cloning, indistinguishability, but it cannot reproduce two very fundamental things. One is this non-locality and the contextuality. And you see this, it is a maximally shy epistemic theory, but it cannot reproduce this analogous, this feature of contextuality and non-locality. On the other hand, in quantum mechanics, these features are already there. And you see this shy ontology, when the proof, theorem of this particularly second line of theorem, Maroni, Leifer, and then Barrett, they are connecting this with this contextuality of these things. And it is indicating at least some degree of onticity is there. And distinguishability, why people start with distinguishability, let's put the question in this way. I say, I give you a red ball and blue ball. I give you this ball, you have to identify this ball. Can you identify it? You just open this. We are assuming we are not color blind. So we can see this ball, yes, it is a red ball. Now let's put the question in this way. I have prepared two boxes. In one box, I give this information to you. In one box, there are 50 red ball and 50 black ball. And in another box, there are 50 black ball and 50 yellow ball. Now, and the box from the outside is identical. Now I give this box to you and I ask you, okay, just pick one ball and tell me what box I have given to you. Can you tell that perfectly always? You cannot. But are you astonished by this? Because I have an explanation, okay, I have an ignorance kind of explanation. So somebody can say, okay, quantum mechanics, we see that, okay, Ket 0 state and Ket plus state, they cannot be perfectly distinguishable given one copy. Maybe this Ket 0 and Ket plus are like this box. something deeper, that the full information is there, something that is going on. If we can come up with such an explanation, then indistinguishability of non-orthogonal quantum state is not as striking. It is like classical, these kind of things. But if he fails to give such an explanation, then isn't it striking? So this ontology, from looking it from indistinguishability, it is revealing that striking feature in a sense.
Okay. You have another question? Yeah.
Yeah, may I ask a quick question to Matthew? So you mentioned that the existence or the observation of interference does not necessarily point to a psi-ontic theory over a psi-epistemic theory. Could you please just elaborate on that? I'm very curious.
Okay, so these questions are always a bit subtle because when somebody says interference, quantum interference to me, they don't always mean the same thing. Okay, what I'm thinking of is the kind of arguments that you find in Feynman, right? So where you say, well, you can do it with the Mach-Zehnder interferometer, where you either have a detector in the path or you don't, and then somehow the particle has to decide whether to behave like a wave or a particle. So this kind of thing is what I'm talking about. And all of that can be done with a Mach-Zehnder interferometer, with just a 50-50 beam splitters and detectors. It's not the full range of quantum interference, right? To get the full range of quantum interference, I have to consider arbitrary phase shifts and get the full visibility fringes. I'm saying, look at the stuff that people say is problematic, right? Look at the stuff that Feynman claims was problematic, that contained the only mystery, what arguments he gave, and what other people have given. I claim that those things exist in something like the Speck-and-Stoy theory, and we have a paper called Why Interference Does Not, I can't remember, Why Interference Does Not something, where we give that model. And so we give the explanations, sort of a Speck-and-Stoy theory type explanation of this kind of Mach-Zehnder interferometry, and we extend it to things like the quantum eraser and the Ellertz-Weidman bomb and things like that. Now, of course, that isn't all of quantum interference. So when you say quantum interference to me, you could turn around and say, well, I didn't mean that. I meant, the full cosine interference fringes or whatever. And when you go to that, then you can find things that are genuinely non-classical. Okay, so we have, in follow-up papers, we looked at, for example, the sort of which path distinguishability versus interference visibility trade-offs, so these wave-particle trade-offs, and we found that the form that they take in quantum mechanics couldn't be reproduced by a non-contextual ontological model. And so that indicates that when you go outside of just the sort of 50-50 beam splitter, pi phase shifter kind of framework, then you're going to find aspects of quantum interference. That's not too surprising because, to some degree, a Mach-Zehnder interferometer is a qubit, right? You can do any unitary operation with sufficiently many optical elements, right? So to the extent that there's any non-classicality in a qubit, so preparation contextuality, for instance, you're going to find it in some experimental setup. So when you want to say something like interference is classical or non-classical, you need to be very clear on which aspects you're talking about and what are you trying to reproduce. So the claim is just that there's this set of things that's been pointed to as genuinely problematic and as like genuinely indicating the failure of classicality, and that stuff isn't. Other stuff is, right? So that's what the claim is. But anyway, I can point you to those papers if you want to know more.
Thank you.
Yes, please.
Yeah, this question is particularly to Matthew. So I don't know how well I can formulate the question. So it is more from a philosophical kind of things. So if we try to, there could be two approaches to understand the nature in rest and nature in motion. So, but it is a very old debate also. Like if Geno's view, nature is snapshot kind of thing, but that is very uninteresting. A better understanding is to nature, trying to understand nature in its motion. So now that comes this, okay, that I have when we try to theory building, there are two aspects, kinematics and the dynamics. Now, so far all this ontology, what we are trying to give, that is on the kinematics only so far. So is there any approach or any try to, okay, how to build the ontology based, means considering both these aspects, kinematics as well as dynamics. Not like this Hardy thinks is, okay, it is kinematics, then under dynamics how it evolves, that is the things. But in my theory building, I itself, from the very beginning, I want to build the ontology looking to these two, kinematics, dynamics, or rest motion, this contradictory motion, consider both them together. Is there any approach, or what do you feelings?
Okay, you want to talk metaphysics? We can talk metaphysics. Right, so I mean, there's a few things to say here. Like, the most straightforward thing to say is, of course, there is modeling of dynamics in this framework. It's just that it's not always used. In fact, it's hardly used ever because there's enough interesting stuff to do with just prepare and measure things. But it does exist. The other thing to say is that from my own personal view, I'm not sure it makes much of a difference, right? I'm not a huge fan of the kinematics dynamics distinction. I more or less believe in the block universe. I believe in sort of a Humean view of laws, which basically means that they're just summaries of what actually happens as opposed to having causal dispositional powers. So for me, like, metaphysically, the world is this sort of tapestry of events in 4 dimensions. And that's the thing I've got to understand. I don't make a strong distinction between things that are dynamical or non-dynamical, because I know that that's not everybody's view. So from my point of view, I'm not really worried too much about this distinction. But that's just me, though. It does mean that I would prefer to be working in ontological frameworks that foreground the 4-dimensional space-time picture, though. And I have spent some time thinking about that and working on that. It's kind of a work in progress. Like, for years, I've had this half-completed paper about block universe ontological models. So I am thinking along those lines. But yeah, I recognize that from other points of view, it makes more sense to think about these things.
Thank you. Devashish.
Yeah, so I have 2 questions. So first one is to all of you. So so how should we interpret the theorem by Kolbeck and Renner? And if we want to compare with the PBR theorem, like, is it possible to say, like, which is stronger in the sense that it involves weaker assumptions or not? Yeah.
I don't know whether how can they be compared, but one thing I am trying to tell, that if you look at Kolbeck-Renner, their claim, I forget their claim, but if you look at the paper in PRL, that result I showed, that even if you go to the lambda level, local marginals are half up. Then at least, as I wrote, that at least you get 2 states, actually a class of states you can see in the Leifer's paper, but consider 2 states, phi plus and 0, 0, then they are ontologically distinct. And here the assumption that has been used, that is accepted in quantum mechanics also, there is no signaling condition or parameter independence. But it cannot be, I don't think whether it can be directly compared with PBR, because PBR is using preparation independence. So in my slide, I myself wrote that I want a discussion on the status of this preparation independence. From my side, that's all.
So, but I'm saying that is for just to inform you that on Kolbeck-Renner, so I find that there are lots of debate with Girardi and probably with even Ballantyne also in his work They have, not the spiral paper, but the next paper, this nature communication, size, the complete, these things. Both of them, lots of criticism are there. Maybe that could give you a better idea what is going on there. But they are probably use stronger assumption there, too much stronger assumption they are using. Yeah, if you can.
Okay, so you identified the issue that's going to cause a fight. Well done. So, because if you've read my review article, you'll notice that I came to a very different conclusion, which is my conclusion was that for proving the reality of the wave function, the PBR assumptions are okay, fairly reasonable, but the Kolbeck-Renner assumptions are not reasonable at all. And here's the reason for that. So first of all, I don't like to think of parameter independence as no signaling. It is a no signaling condition, but it's no, if you knew the state of reality, if you could observe the full state of reality, then you wouldn't see any signaling. Now, a lot of realist interpretations don't satisfy that. De Broglie-Bohm doesn't satisfy that. De Broglie-Bohm violates parameter independence, but it satisfies no signaling. And the reason it satisfies no signaling is because you don't have full information about the state. So I think it's good to keep those two things distinct. And the second thing is, okay, so relatedly, if our goal in life is to try and prove the reality of the wave function, what you want to do is make assumptions that hold for the viable theories that we know about that have a real wave function. So if I make an assumption, for instance, that isn't satisfied by de Broglie-Bohm, and I prove the reality of the wave function based on that, that's not going to seem very good to the Bohmians, because they'll say, well, you've proved something that's true of our theory, but not with assumptions that are compatible with our theory. So I don't really want to do that. If I have like a canonical example of a theory that at least some people believe in, and that has the reality of the wave function, I want to make assumptions that are compatible with that. Same kind of thing was a motivation for Bell, right? You know, if even before he'd written down local causality, he'd made an assumption about the nature of reality that ruled out Bohmian mechanics, he probably wouldn't have been happy with that. So the fact of the matter is the preparation independence postulate is satisfied by de Broglie-Bohm theory, and parameter independence is not. So, you know, for that reason alone, I would say the PBR assumptions are better. Now, as regards the more general Kolbeck-Renner theorem, so this thing about can you have additional variables that help you in predicting things, it's a little bit disappointing. So Renato Renner, as you probably know, has produced multiple no-go theorems, all of which are interesting, and all of which are very, very terribly written up, because he refuses to use a language that is amenable to people to the quantum foundations community. He makes up his own terminology, and people get the wrong end of the stick. Maybe even he gets the wrong end of the stick. The Kolbeck-Renner theorem itself is kind of a beautiful thing. So what I view it as is like, okay, to prove Bell's theorem, you need parameter independence and outcome independence. Now you have a question. What can I prove if I drop outcome independence, keeping parameter independence? And the answer is you can prove that a theory like that cannot make predictions any more fine-grained than quantum mechanics. So you don't say that those theories are ruled out, but the predictions have to be the quantum predictions. So that's all. That's quite a nice, elegant result as far as I'm concerned. If you sell it the way they sell it, of course it's going to be controversial. But to me, that's an interesting result. And you can, talking about another controversial no-go theorem, you can view it as a result that supersedes the free will theorem. So Koch and Conway free will theorem, they assume parameter independence and determinism. And they conclude that you must rule out determinism. Well, Kolbeck-Renner assumes parameter independence, but doesn't assume determinism. And they say, well, the only thing you can have is the quantum mechanical predictions. So to some degree, now I don't need the free will theorem because this theorem's stronger than that. So if you think the free will theorem is interesting, which not everybody does, you should definitely think Kolbeck-Renner is interesting. So I'm a strong defender of the result, not as a proof of the reality of the wave function, but just the result as it is. It's kind of like, I want to take Bell's theorem, I want to see what I can prove just with parameter independence, and that's it. And so I think that's perfectly interesting on its own without all of the surrounding controversy.
Should we bring this session? Oh, there's a question there.
Okay. I'm Surajit from Calcutta University. Suppose there are two statements. First one, psi is part of reality and determine the distribution of lambda. And second one, psi is just a mathematical tool which encodes incomplete or approximate information about distribution of lambda. Are they different? Because according to the second statement, it is possible that there are underlying ontological model as a result of which nature actually deviates from quantum mechanics in some yet unknown situation. And we can define a characteristics function psi which approximately encodes information of the mixture of ontic state. So, from the second point of view, it may be possible that psi is approximately ontic and also incomplete. So, are these two statements different?
I think we are trying to understand quantum mechanics and its epistemic ontic role. So better to proceed without putting these approximation and all these things. Better to first at least not to introduce this approximation. But I think that...
Yeah, so I'm not 100% sure I understand the distinction you're making, but let me reiterate something I said a bit earlier, which is actually we're not trying to understand the nature of reality, we're trying to understand what's the best explanatory structure for quantum theory itself. Okay, so from that point of view, we're just going to look at plain quantum theory. Of course, it's true that we never confirm quantum theory to 100% accuracy, and there could be deviations. And in fact, when you try to experimentally prove the reality of the wave function, you try to do an experiment on the PBR theorem, for instance, which people have done, then you will find that the probabilities that are supposed to be zero aren't exactly zero. You sometimes get that measurement outcome. So you actually only ever prove approximate Scientology, even if you make an assumption. You go out and do an experiment, you approximately get the right results. So you prove something like the amount of overlap is small, not that the amount of overlap is zero. I don't know if that fully addresses your question, but yeah, I mean, that's all I have to say now. Yeah.
Okay, and the next question. In all these hidden variable theory, whether it is psi-ontic or psi-epistemic, the extra information, lambda, may be anything. It may be the information related to some yet undiscovered beyond space-time structure also, which will explain in future why we have some kind of action at a distance within some ontological level in quantum non-signaling non-locality. So in this kind of investigation about psi-ontic and psi-epistemic, we are not bothered about non-locality in the ontological model. Is this correct?
I didn't understand fully your question, but let me clear 2 points. If you consider psi-ontic model, which can be psi-complete or psi and lambda both are there, then actually to prove the non-locality of this ontological theory, you even need not invoke Bell's inequality, violation of Bell's inequality. It will be just using ontic ontology, you can prove that it is non-local. But if it is psi-epistemic, and even if it is not maximally psi-epistemic, even then, using maximally entangled state, you can show that it is non-local. But if it is maximally psi-epistemic, then you need to invoke violation of Bell's inequality. So, only now, to show non-locality of quantum mechanics, you have to invoke violation of Bell's inequality if the theory is status of psi is not maximally psi-epistemic. This is the thing. Then I think, yeah.
Okay, thank you very much. Shall we? Oh, there is a question still. Yeah.
Hi. No, it's fine. So it's only elaborating on the same thing.
So, yeah, I'm Shom from INL, Portugal. So, my question is, okay, not directly related to ontology or epistemic, but probably it is. So, Spickens had a paper where they said that violation of Bell inequality implies violation of no fine-tuning. So,
no fine-tuning.
So now I just want to understand that, okay, what's the, like, how would we interpret this result in the language of the, psiontic, psi-epistemic theory?
So, from my point of view, and not everybody's going to agree, but from my point of view, all the good no-go theorems, all the no-go theorems that are interesting are no fine-tuning theorems in one sense or another. So I wrote a paper about a framework for understanding fine-tunings. Spickens has a different paper, and we don't quite agree on which is the better framework, but there you go. But my point of view is you can view being psiontic as a fine-tuning, because how do we understand fine-tunings? We say, okay, let's look at the operational predictions of the theory. They have some property, okay? Why does that property hold? One answer to why that property holds is that the same or the analogous property holds at the fundamental level. Another possible explanation is that it doesn't hold at the fundamental level, but since we don't know the fundamental state of reality, we have to average over it, and when we average over it, that property gets washed out. So, for example, at the fundamental level, perhaps there's signaling, right? Parameter independence is violated. When we average over lambda, we can't use that to signal. And you might say, okay, there's a fine-tuning there because I have to make sure that my probabilities over lambda are set in a very precise way in order to wash that possibility out. Now, all non-orthogonal pure states are indistinguishable, right? What's an explanation for that? The underlying states are indistinguishable, right? The underlying epistemic states are indistinguishable. It could be that they're not. But then when you average over what we know about them, that possibility is washed out. The flavor of the argument is the same. If that quantum state is there, why is there absolutely no way whatsoever that we can determine what it is? It will be okay if most ways of looking at it didn't tell us, but we know, or if quantum theory is true, there's absolutely no way of telling the difference. So there's a distinction that apparently exists in reality that is completely undetectable. And that's a fine-tuning. So for me, being psiontic is fine-tuned. So let me just make one final comment about that. A lot of people like Everett because they say Everett isn't fine-tuned. There's no non-locality. Like, being psiontic is a fine-tuning. So Everett is fine-tuned. That may be controversial, but there you go.
Okay, thank you very much. Oh, there's still a question. Yeah, please. Can you pass it on?
Yeah, hi. So I just want to add a comment regarding one of the previous points that was raised regarding if there is an implication or a derivation that can be had about one of the postulates of quantum theory and these ontological models. And this has a connection with the previous question raised about fine-tuning. So in the de Broglie theory, the Bond rule is not treated as a postulate. So the initial distribution of the configurations is arbitrary. So the theory as such allows for signaling correlations. But if you follow through the dynamics, for an arbitrary distribution, what you eventually get is a relaxation to the bound rule. So the question about the postulate is answered in this way, that you can derive the bound rule in de Broglie theory. And it also addresses the question about the fine-tuning, because it's a syontic theory after all. The quantum state is real in de Broglie or pilot wave, but the theory is not fine-tuned because it does allow for an experimental signature of the signaling correlations in exotic regimes. Yeah.
Thank you.
Yeah, just let me follow up. I totally agree with that. When I say I don't like things that are fine-tuned, it doesn't mean that the correct theory of nature doesn't have that kind of property. It just means that if it exists, I feel like it needs an explanation. That explanation could be that the fine-tuning really isn't there. It could also be, as in de Broglie theory, you have a dynamical explanation. In order to believe that dynamical explanation, though, I have to believe that at the fundamental level there's signaling, and that it's likely that that signaling will be observed somewhere. That's very bold. I mean, it's bold of you to make that kind of claim, and I can understand why most physicists don't want to agree with that, right? Because it seems like we're not going to see non-local signaling fundamentally. But it's the correct kind of approach. You say, okay, there's a fine-tuning, then I need to either explain it dynamically or get rid of it. You're happy to explain it dynamically, you've given an explanation. So that satisfies that requirement. Yeah.
But one thing is there in Bohm's model, this position distribution is mod psi x mod of psi x square. So there is something. Probability of, so Bohm model is psi comma x. X is considered to be the position of the particle. So distribution of x is square of the mod of psi. That is there.
Yeah, that is true as an equilibrium condition. Yeah.
Otherwise,
right.
So that's why now it becomes no signaling theory.
Yes, under that condition.
Yeah.
For arbitrary distributions which are not mod psi square, the theory does have signaling correlations. Yeah. And one can observe that for an arbitrary distribution, you would have a relaxation in general to the mod psi square distribution. So you'd start from a signaling correlations, and then you end up in the no signaling sector. Yeah. So you would have a dynamical explanation, as Matt was pointing out, for the bound rule, and also for why we observe this apparent fine-tuning in nature. Yeah.
Okay, thank you very much. This was a very exciting session. Now we'll have lunch break, of course, and we'll reassemble at 2:30, but I have to outline what happens. When we write a paper, we of course write a conclusion section. So this will be the conclusion section of the conference, in which we'll have all the remaining speakers, some have left, speakers and the session chairs on stage, and we'll request everybody to outline in about 5 minutes the take-home messages. Because when we go back, we would like to reminisce what you learned, we'd like to plan what we do, and for that it is necessary to have some kind of a take-home message, things that are interesting, things that are on the horizon, things that are likely to become important in the coming years, our take on that, and then we'll end. So the next session is going to be important and interesting. We'll assemble at 2:30. Thank you. Yeah.